Today I'd like to tell you a little bit about a major survey that's been going on for a couple years called CANDELS. And my role is not to substitute for the several speakers that have already given you excellent CANDELS results from Pascal, for example, and Guillermo Barro and Yiqing Guo, but to give you just a flavor of the type of data that you can actually access, because this is a very public set of data. So, and I'd also like to just mention a few highlights from the survey that were not mentioned here because the key authors were not able to attend this particular workshop. Now, I'll give you a brief overview of the CANDELS survey. The key thing you should take away is that last week, the survey is finished. This was a 3-year project of 900 orbits and completed 5 fields, and it's done. But I'd like to give you an overview of some of the science goals, strategy, and what's been happening with the survey. In terms of highlights, as you'll see, the data is so rich, and even though our team is enormous, there's a huge amount of science that can be done. I would only be able to give you a flavor of the type of data, the type of science that you can approach with the kind of quality of data, and especially its multiple survey emphasis in these few fields. And in particular, I'd like to mention talk about the morphologies of galaxies, the redshift of 2, so what we call cosmic noon, the redshift of 2 era. I'd like to mention something about both the galaxies and about the AGN host. And then I'll give you a summary of my talk. CANDELS itself is an acronym. It was purposely spelled incorrectly with an E in order to prevent searches with CANDELS giving you 7 million hits. You now can actually go right to CANDELS, put down with an ELS. It actually does stand for something that's relevant. It's Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey. This was one of the chosen multi-cycle Treasury surveys that was sponsored by HST a few years ago. There are, as I said, a large team, about 175 members. We occupy currently 45 institutions. I suspect a few more. I think some of our postdocs have moved on to new institutions, and it occupies about 12 countries. The PIs are Sandy Faber, who unfortunately was not able to give a talk. She's busy with other matters now, and Harry Ferguson. And then there's several people that we call the builders. These are the people that really provided the core infrastructure, and they should be given special recognition, including Adam Rees, Steve Rodney, Norm Grogan, Dale Kuchevsky, Anton Kokomer, and Kamsten Lai. None of them are actually here other than Sandy in the audience. The CANDELS in a nutshell is basically it's an optical infrared survey. It covers about 1/4 degree, and that 1/4 degree is spread among 5 fields. But these are not just representative in terms of the sky. They are exceptional. They're truly exceptional in the sense that they cover the very deepest fields that have been observed at other wave bands and other modes of observations. And they are definitely currently the best reference fields for studies of the distant universe. One may argue that perhaps behind a cluster through lensing, you might be able to get a little bit of this magnification and therefore reach maybe the faintest objects. But in terms of the entire panoply of wavelength information, spectroscopic information, the tools, et cetera, the Mach catalog, et cetera, these fields are, I think, will not be beaten for at least a decade and well into the JWST era. The critical new piece of information that came out of the CANDELS survey is the infrared images. And I'll show you in a moment how important they are to study this very special time that we call cosmic noon. And because of this ability to work in concert, that means CANDELS itself comes from HST, has the optical and infrared imaging from that telescope, but there are many other telescopes that can add additional information, and they provide the critical information a lot of times to get the right science out. In addition to the galaxies and the AGNs, there's actually a supernova component. I won't talk about that. There's actually a very deep ultraviolet component in the Goods North field. It's a very small fraction of our entire survey, but it does provide one little peek at a different wavelength with HST quality data. Now, what can we do with this near infrared? The best way to convey this is to show you what you would see with a very decent, I think, 1 or 2 orbit optical, in this particular case, the I-band Hubble Space Telescope. And you see here a panel of 8 objects, and you say, okay, decent. They look like scrawny little galaxies, as you might expect. But if you use the infrared camera to exactly the same number of orbits, the same depth, this is what you would see. And here I've actually divided these 8 into 3 categories. The objects that we consider with the new infrared information, which is the H-band 1.6 micron, you see that we can see the spheroids now, which would be virtually invisible in the optical. The near infrared for the disks, you can see them quite clearly. They're edge-on systems. They look flat. They have little spiral arm signatures, et cetera. And that shows for the next 3 that clearly the infrared is extremely powerful. And it even shows you what we call hidden mergers, things which if you looked at the original images, they're probably single galaxies, a little scruffy with some clumps, but clearly if you can see 2 or major asymmetries, you would say, yes, we have in fact evidence for more than one galaxy, showing signatures of interaction. And this now shows you the full set of data that we would be collecting through our CANDELS program. We collect the V and Z data that comes from the optical camera, the advanced camera for surveys, ACS. And then we have Y, J, and H that comes from the new near-infrared camera, the wide field camera 3. And together you can make, for example, very pretty pictures using any 3 of those bands. It gives you an idea of the richness of the color substructure within galaxies, obviously intensity and shapes and other information. Now the fields that we've chosen was a challenge. We had to pick, not too many fields because we had to get it within some number of orbits. We turned out that we missed a few, perhaps in the north. I mean, one could argue there's a field that they studied by the X-ray group. Rosat and others have been studying very deeply, but we excluded that. There's some others as well. But we ended up with certainly the deepest, densest, well-studied fields. They are the 2 Goods North fields. They are the Cosmos field. There would be the Aegis field, which is in the north, not accessible to the southern telescopes. And then there's one that is accessible to both hemispheres called the Ultra Deep Survey field that has extremely deep near-infrared imaging. Now the total sample will probably recover something like 250,000 galaxies, 250,000 galaxies. Well, gee, you don't need that many. We can, Reinhardt shows us a few dozen and get all kinds of cool science from it if you put in enough effort. Well, it turns out, as you can see just from this conference, there's enormous variety of the properties of galaxies, everything from mass, size, shapes, clumpiness, their environments, and all these things. When you slice and dice them and you spread them out over time in terms of redshifts, you immediately need a large sample. And so I think in the end, we will appreciate that we have as many as 250,000, and even that may not be enough. A good example is Sloan. People thought, wow, who needs 1 million galaxies? Well, we're still studying Sloan, and we're still learning a lot of things. And so I think when you get into higher statistical precision, and you need rare subsamples, whether they're AGNs or maybe the densest galaxies, et cetera, you need these large samples. Our volume is not fantastic, but we're going extremely deep. It is what we call a wedding cake structure in terms of our survey. We have a small area that's observed extremely deeply, a medium size that's somewhat wider, and then a much larger area that's even shallower in depth. The key thing to remember is this data is public. It's public immediately for those people like Pascal's team. They just take it right off almost right off when the telescope collects it. They process it with their own software. We, of course, as a community service, will process the data best we can. We make mosaics. We make catalogs. We'll have the theorists with our team will make mock catalogs for these fields, and they provide a lot of the fundamental foundation for additional science that you can get either by adding additional data or otherwise. Now, as I mentioned before, our major achievement, we did finish the survey as of last week. That means all the data has now been collected by Hubble Space Telescope. It is now in the process of being developed into mosaics, catalogs, and other science products. I mentioned this aspect about complementing. That's without the I, but the E. Adding additional information to the data that we're collecting. A lot of it was actually collected before the CANDELS survey. In fact, we justified the CANDELS survey because there was extremely deep IRAC observations from the Spitzer telescope. There were already extremely deep Chandra data. There's already extremely deep data in Spitzer MIPS, for example. So there are good reasons for choosing these fields. Here's an example of why it's important to get multi-wavelength. You'll see a very different view. Here's one with Hubble using 0.6, which is optical, 1.25, which is the near-infrared, and 1.6, which is the farthest red that we observe with HST. And here's an image. You see lots of objects in this field. This is what you see with Chandra. And this one was, I believe, a 4 megasecond, 4 million second exposure. This is the very deepest in Good South. And you can see that, you see a few sources. Now, how do they stand out in terms of context of other objects? Go to a far higher, a larger wavelength or lower energy range. And you can hear in the mid-infrared with Spitzer, with the IRAC. And you can see that those sources go back and forth. Here's the Chandra sources. And here are the Spitzer sources. You can see that there's a very excellent correspondence. In fact, I believe that with IRAC, they can observe 100% of all the IRAC, all the Chandra sources. Spitzer also has even longer wavelengths. And there you immediately see something that's clear as you go to longer wavelengths. Resolution decreases. So while HST is fantastic in terms of spatial resolution, we do not quite get the complementary or the same balanced high resolution. But they provide very different kinds of information that's important when you're working with the full spectral energy distribution of these objects, whether the AGNs or galaxies. And here's Herschel at 250, 350, 500 total globs, but there are ways, through sophisticated software, we have something called TFIT, that will take all these data with the multi-resolution and try to extract out the very best photometry. That's one of the products that our team is expected to provide to the community. In terms of our basic activities, one of the goals of the survey was not to do everything that's possible, because we can't do it, even with 175 people. So there are a few areas that were put a lot of concentration. One would be the visual classification. That's enormous work. I don't know how many, probably thousands of hours of scientific eyes being used. We take advantage also of the citizen science being done by people all around the world called Galaxy Zoo. We also have quantitative measures. CAS, Genie, M20, Joel Premack, for example, with Jen Lotz developed that with Pierre Madao. There's also GalFit, which has been developed by Peng, and then GIM2D by Luke Smart. Those are all being operated by various people on our data set. One of our strengths, I think, is working hard on the spectral energy distribution and trying to get the best photometric redshifts that we can. And here we have 13 different groups with different codes and different assumptions about spectral energy distributions, including AGN or not including AGN, including Michelin or not. And they're all working together trying to see what we can do in terms of getting the very best of this information. So you can expect our team to provide you superior data in these areas. The other part of our survey that I find extremely helpful and, in fact, critical to our understanding of the data, of course, is our theory group. Not only do they have these semi-analytic models and hydrodynamic codes, you saw Yichin's simulations. I think Guillermo showed you what some of the simulations tell you about nuggets and clumps, et cetera. There's also going to be mock catalogs that give you a way to assess the incompleteness of these surveys. So for those who are interested in a better understanding of biases and especially for selection, for example, Tomer's experiments with groups, et cetera, it's critical that you have this information as well. And then, of course, we have the usual outreach and social things. We have blogs and we have teacher workshops, and I think there's an iPhone app that Dale has been working on. Now, in terms of science goals, we have many here. I've broken them down into major categories. These are ones actually listed on the web, so they're not new. Cosmic Dawn was very well covered by Pascal Oesch yesterday. These are high redshift galaxies. Because we're looking in the far red, and we have IRAC, et cetera, we could study that. I'm not going to say anything more about that. Distant supernova is proto-dark energy. I'm going to skip that as well. That's work being done by Adam Rees and Steve Rodney and their team. The deep ultraviolet studies, I mentioned that there's a little bit of that. We could study high redshift dwarfs, Lyman break galaxies, and even the escape fraction from Lyman continuum. And here it's only in Goods North. I'm going to skip that because the data was just collected in spring, and I don't know of any papers that's forthcoming from that. The sweet spot for science, and we could do that without the full survey, we didn't have to wait till last week to begin this, was the study we call Cosmic New. This is the redshift roughly 1 to 4, a very key time when galaxies appear to be going through major transitions in their morphology, in the star formation rate, in the buildup of stellar mass, perhaps in their environmental properties, et cetera. It's also a key period for AGNs. That seems to also be a time when something's very much happening, probably because of gas. I mean, Reinhardt's talk and Linda's talk and others indicate that gas is a critical component, and that indeed is a period when a lot of gas is probably inflowing, perhaps through cold flows that Havishai and others have been promoting for quite a long time. Among the, looks to me like 7 different subcategories that we have on our web, I've highlighted those in green that I'll just say a few things about in terms of a little bit of the science that's been done by a few members of our team. They would include, for example, study of bulges and disks and galaxy subclumps. I'd like to emphasize there's a strong interest also in the AGNs and their host galaxies. And we try to include the very deep Chandra data and multi-wavelength so we can get after indications, for example, amount of dust of obscuration. Now, it's actually now 34. I think another paper was just submitted yesterday. But we have lots of papers. You just go to our site. You can find them. You can click on them, go to them. Hopefully this will increase over time. More importantly, I hope these candles just represents our team, but we're hoping the whole world and the theorists and observers alike will take advantage of the superb data that comes from these fields. Not just the candles data, but this complementary data from GRISM called 3D HST. There's, as I said, Chandra, Spitzer, Herschel, et cetera. And there's probably going to be wonderful work being done by, what's that, Numa, or whatever it is, the CO and ALMA, et cetera. Now, in terms of the highlights that I mentioned today, here are the few categories and their associated lead authors. As you see, most of the dates are pretty recent, so hopefully they're somewhat new from last year. I'll talk about the morphologies of the quiescent versus star forming, and talk about the emergence of the bulges, and I'll complement or add on, follow up on some of what Yiqing had said, and then mainly I'd like to focus on the AGN host galaxies. Here I think we've had a change in our view of what's perhaps really happening here from even a year ago, work being done by Jen Donnelly, Dale Kuchevsky, and Cyprian Rangel. So first of all, talk about the massive galaxies around redshift 2. These are typically 10 to the, a few times 10 to the 10 solar masses and greater. How do they relate to each other? Here's a diagram of two axes that involves what they call the Gini M20. Gini is an indication of how much concentration, so that of the resources being used by economics, et cetera. In the case of galaxy, it means if it's really concentrated, it's got a high Gini index. If it's few, if it's evenly spread out, it's a low value. The key thing to note here, and the M20, by the way, gives you a sense of also the distribution of the information. Don't worry about that. The key thing is that these are measured quantitatively from the images, and when you look at galaxies which are either inactive, go back. These are the ones that are very active with star formation. These are ones that are passive. You see that their structure, in fact, is visibly quite different. Here, in fact, are the X-ray distributions of the same objects. Here's the key thing. Here is just note: we have real information about the morphologies of galaxies, even though they're redshift 2. This is the key information that is new for us. Is the infrared, and this is work that was done by Wang. Now, it's not too surprising what we know about locally, but the passive 24 micron faint, this is from Spitzer, basically means the star formation rate is low, tend to be very compact, they're spheroidal in shape. The star forming ones tend to be more extended and more disk-like. Actually not that different from our local universe. And then if you look at the correlation of star formation and their actual shape, you find that that the correlation is actually with star formation, actually the shape of the galaxies less than the mass. So if you take the same mass of a mass for a set of galaxies, you will find that the shape actually does affect the star formation rates. The next figure I'd like to show you comes from the work of two papers actually, from Victoria Bruce and I've got Mortlock's first name, both of their papers. But the bottom line is that for the very massive galaxies here, we're talking about 10 to 11. So these are huge, many times bigger than our Milky Way at that time. So we're talking about things that today would be enormous if they have any buildup. And this is a pretty simple diagram. It basically shows you the, redshift at the lower axis from 1 to about 3. That's our sweet spot in terms of cosmic noon. Here's a fraction of the total population. And you can see that those which are bulge dominated, which go greater than 50%, are shown in red. And here are the ones that are for disks in blue. And you can see that somewhere around redshift of 1.5 to 2, certainly around the redshift of 2, there's a transition so that the bulges become more dominant at lower redshifts. Again, not a big surprise, but it's good to confirm this with actual quantitative data, and we can actually make these measurements. Now, one of the interesting aspects is we did find a few passive galaxies which are actually, as far as we can tell, almost pure disks. That's interesting because if, in fact, these massive galaxies are a result of major mergers, then how do you get something that's sort of disk-like when you have something as massive as this? So it may say something about what the quenching process is involved, whether mergers are involved, et cetera. And so the relative numbers of different kinds of galaxies, disk-like, bulge-like, and those all in between are important. And so in terms of the era of these very massive disks, it's probably somewhere around redshift 2 to 3. How much time? Oh, okay. I'm going to move on very quickly. I'm going to skip the clumpy disk because Yi-Ching did such a good job. I originally thought he was going to talk about this. I'm going to just skip that section. And I will then move on to what I think is an interesting result with regard to the host galaxies of the AGNs. And here, Dale Kachevsky last year found that, gee, the AGN hosts are not disturbed. They, in fact, if you look at them, have a lot of disks. This is not quite our view of what these hosts should be like. And that was somewhat of a surprise. So it was not the normal standard paradigm for these host galaxies, so it might be internally driven. However, over the last year, the X-ray group have been working very hard. They've had better fits in terms of the spectral energy distribution. They get better estimates of the obscuration. And when you look at the new sample, here's one that redone by Dale. He looks at the Compton thick stuff, and he looks again on the x-axis, the disturbed. He finds, in fact, that these obscured luminous galaxies are, in fact, quite disturbed. So our view has now changed. It could be that we've been missing all this time these very obscured systems, and they, in fact, represent perhaps things closer to what the theorists had been hoping to see evidence for these. When you add the obscuration in, you get a different view of what their morphologies are like. This is, again, supported by the work done by Jen Donnelly. Same thing, it's a little harder to see, but here we have the infrared AGNs. These things were infrared, they're highly obscured, they don't show the X-rays, and here again you find very strong evidence for high asymmetries or high irregularity among those which appear to be the most obscured. I will find this to be too complicated to close because I see that I'm over my time. Just to let you know, along the lines, follow-up of what Guillermo was talking about yesterday, fast track and slow track, red nuggets, et cetera. We have a division here between the extended, compact, high specific star formation actively forming and here not. And we find that in terms of the obscured systems, luminous AGNs are highly obscure, appear to be extremely compact, while the extended ones are less luminous and less obscured. And so, in fact, Cyprian Rangel has now proposed that there's a two-mode, very similar in spirit to what Guillermo was saying, that there may be a fast track and slow track. The other terms in the field have been quasar mode versus radio mode feedback. And so we're now thinking that maybe the AGNs need to be thought of as perhaps a two-path process, very similar to what the galaxies are doing. And so I'm just going to close now with the results and implications. I'm going to skip that part and show you the summary for CANDELS. Thank you.
Questions? Okay, so I have a question about the passive pure disk galaxy.
Yes.
So what are the environments? Are they central galaxies or satellites?
We don't know. At least we have not looked. So that's a separate.
In the local universe,
yes.
You don't see any. You do see passive disks, but they're all satellites.
Right.
So centrals that are passive always have a big bulge.
Well, we have an issue here of trying to figure out what the dust is doing. So to be fair, there's still some question as to whether these are really as disky as they are, because if there's a very highly obscured central bulge, we may be deceived in thinking it's a sort of spheroidless pure disk system. And also the profiles of even spheroidal systems may not be the classic de Vogel-Ayres profile, but they may be actually lower indices. That again can be deceptive. So we're looking for sort of thin things that indicate true disks.